of her career, including the Royal Society of Canada Rutherford Memorial Medal and the AAS Annie Jump-Cannon Award. Her work is like super nice and spans like a wide range of tools, bringing in data from IFP surveys like Manga, as well as absorption line studies, and she, as well as all the observational work, she also pulls in data from simulations and uses machine learning to tie it all together. So I think it's just a really nice, using a wide range of tools to answer the question of how do galaxies form. And today she's going to tell us about galaxy mergers in the nearby universe.
Thank you so much, Laura. Many thanks as well to everyone for accommodating this somewhat unusual time. I'm flying out to Europe tonight, and so I couldn't make the usual afternoon slot. And I hope you all appreciate I brought the warm, sunny weather from Victoria. It's beautiful on the West Coast at the moment, not raining at all. So yes, I'm going to talk today about this sort of extended piece of work that my group have been working on really for probably about a decade now, which, as Laura said, we try to bring together results from simulations, observations, and data science as well. So because this is really an extended piece of work, I have a fairly lengthy list of collaborators, but I did want to highlight at the top of the list here the numerous graduate and undergraduate students who have been working on these projects with us. All right, so there are two main reasons that astronomers would want to study mergers. And why isn't my movie working? That's very strange. All right. Imagine a beautiful movie of interacting galaxies. You've seen these kinds of movies before. So there are two main reasons why astronomers would want to study galaxy mergers. The first is because in our picture of hierarchical structure growth, we think that galaxy mergers are the main mechanism through which structure is built up. So we move from the small dwarf galaxies through mergers, we build up the larger galaxies. And this is a process that not just builds the stellar component of the galaxies, but also their gas reservoirs, their dark matter halos, and also a mechanism through which we grow the central supermassive black hole, because as the galaxies merge, the black holes merge too. So this is one reason that we should be interested in mergers as astronomers. But this is not the reason that I am interested in galaxy mergers. I'm interested in the interaction process for what it actually does to the galaxies during the merger phase of their lifetimes. And so this is a process that has been predicted by simulations to have a really dramatic impact on the stars, the gas, and the black holes of galaxies. And it's nicely encapsulated in this cartoon from a paper by Phil Hopkins a number of years ago. But merger simulations like this one have been done by very many groups using lots of different codes, and the predictions are rather generic. So the idea is that you start off with an isolated galaxy. In this picture, it's a disk galaxy. In any case, think of something that has gas available in it. And if that galaxy is located in an environment in which it has some near neighbors, so for example, it's in a group, or maybe it's in a cluster, the motion of the galaxy around the potential well of that environment brings it into contact from time to time with other galaxies. And so if the orbit is such that it is passing on a bound trajectory, then you can get interactions such as the kind of pictures we're used to seeing from the Hubble Space Telescope, where you can see these very dramatic tidal tails, shells, and other morphologically disturbed features. So these very obvious interaction characteristics we see in the visible light, in the stars, but potentially even more important is what's happening to the gas in these galaxies. So what the simulations predict is going on is that when you have a tidal interaction, you rearrange the matter into non-axisymmetric structures, so you can trigger features such as bars. And so when you have such structures in your galaxy, there is now a mechanism through which the gas feels a torque, it loses angular momentum, and it can flow towards the inner regions of the galaxy. And so in addition to seeing the luminous material redistributed, so the gas also gets redistributed. And in particular, these gas inflows are predicted to trigger a number of dramatic changes internal to the galaxy. So the first change that the simulations predict should happen is that you should get a burst of central star formation, because you're pouring all this extra gas into the middle of the galaxy. The surface density of the gas is increasing, and so you trigger extra star formation. And so here is the prediction from this particular simulation. So this is the time axis along here, where the letter labels correspond to these different pictures that you can read going clockwise around. And so soon after the initial interaction, so after the first pericentric passage, you can see that the galaxies undergo an increase in their star formation rate. And then when they undergo coalescence, there is an even greater peak in the star formation rate. And so potentially you can trigger nuclear starbursts, Euler-type galaxies this way. If the gas can get all the way to the center of the galaxy and accrete onto the central supermassive black hole, then you can trigger an active galactic nucleus, or AGN. And this is what is shown in the lower panel here. So again, as a function of time, what we're looking at now is the change in the accretion rate onto the AGN. And you can see that this mirrors what is happening in the star formation, in the sense that there is a boost in the accretion rate soon after the first pericentric passage, and an even greater peak at coalescence. And so if the accretion rates are high enough, you can start to trigger very violent AGNs, such as quasars. The combination of these two events, so the triggering of star formation and the fueling of the AGN, have the potential to create a lot of energy. And that feedback of energy into the galaxy is predicted to then impact the remaining gas left in that galaxy. Yes?
In time disruption events of stars, the mass accretion rate follows at T⁻⁵. So do you see a similar pattern in time disruption of galaxies?
Sorry, say that again?
So in time disruption of stars, of individual stars.
Oh, in time, right.
By supermassive black holes, you see luminosity or mass accretion rate that declines as T⁻⁵. So I'm wondering if you see the same pattern.
This depends very much on the prescription in an individual simulation as to how they get the gas all the way down there. So the simulations tend not to have a truly physical way of getting the gas all the way onto the black hole. They tend to get it down to within a few parsecs and then put it on. So I would say what happens, the details of this depend quite a lot on the way the simulation is set up. You can ask me again when we look at the observations again. But in terms of the simulations, that's the response. So the feedback we get from the AGN and the star formation has the potential, at least as predicted from the simulations, to impact the remaining gas reservoir. It can heat up the gas, it can ionize the gas, and potentially it can completely remove the gas from the galaxy. So this is sometimes termed the blowout phase. And so if you either heat or remove the gas, you can no longer readily form stars. And so in the final stages of this merger life cycle, the prediction is that your merger remnant will not only be morphologically transformed into an elliptical, it will also have its star formation quenched. So as observers, we would like to be able to test these simulations. And that's what we've spent the last decade or so in my group testing, each of these in separate individual phases. So that's what I'd like to tell you about today. So the bread and butter of this work has been using large surveys of galaxies in the nearby universe. And a lot of our work has been based on the Sloan Digital Sky Survey, but as you'll see through the talk, this is now added to with various all-sky multi-wavelength surveys and also PI follow-up that we have also done. So the first step in this is obviously to identify a sample of mergers. We want to test how the mergers are different to isolated galaxies to see whether these simulations are making accurate predictions. So we need our merger sample. So this comes in two parts. The first part of the merger sample is when the galaxies are still in the pair phase. So they haven't fully coalesced yet. They're in this interacting regime. So this is very straightforward to select from a large spectroscopic survey such as Sloan, because you can find galaxies that are both close on the sky from the imaging survey, and because you have the spectra, you can also require that they are close in redshift or in velocity space. This allows you to try to remove contamination from projected pairs. So this is how we sort of did our original selection. So taking pairs within 80 kiloparsecs of one another, 300 kilometers a second. We also put a mass ratio cut in there of 1 to 10. When you do that, you get some 14,000 galaxies out. So these are the galaxies that constitute the pairs sample. Now, a very important part of all the experiments I'm going to describe to you today is the construction of a control sample. So we need to set up our experiment such that we can measure a given property in our mergers and compare it to what we expect would have happened if that galaxy was in isolation. So we need to have this control sample. You can think of it as an isolated or a field sample, but I'm going to refer to it as a control sample. And it turns out that results are very sensitive to how you do this. If you don't do this properly, you get some very strange results. So I just want to spend a few moments describing how we do this control sample. So for every galaxy that is in a pair or in a merger, we look at all of the other galaxies that are in Sloan that are not in mergers. So that's a pool of some 650,000 galaxies that are not in mergers. And we find, for any individual paired galaxy, we find all of the controls that have the same stellar mass, the same redshift, and they're in the same kind of local environment. So we're trying to match for other properties that might otherwise be affecting the galaxy, such as star formation rate. So then what we can do is, from the hundreds or sometimes thousands of bespoke controls that we have for every paired galaxy, we can take the average of its control and compare any given property to the paired galaxy. The second part of the sample is the post-coalescence or post-merger regime. So if you recall, the simulations predict that this is when the fireworks really get going. So we want to make sure that we sample this phase in our observations. So this is a sample that is less trivial to construct. It's difficult to do this in an automated way, unlike the pairs. So what we've done is taken this post-merger sample from essentially from Galaxy Zoo. So this is a much smaller sample. It's much more labor intensive to go through and visually classify the galaxies, but we end up with a sample that we can be confident is very pure. We've checked all of these ourselves by our eye as well, and you can see that these post-mergers are characterized by the strong visual disturbances, so tidal streams, tails, and shells. And then we have a control sample that's matched in exactly the same way. So now we have our samples in hand. We're ready to start the testing of the simulations. So the first thing we'll do is test this very basic prediction that interactions should render the galaxies more asymmetric, that they should start to show these morphological disturbances. So what I'm showing you here, and this is a figure type that we're going to see repeatedly in this talk, so we'll just take a moment to orient, is on the x-axis we have the projected separation of the pairs. So you can basically read this from right to left as the galaxies get closer and closer together. Now, of course, this is not perfectly linear because the galaxies come in, they have a close pass, they move out a bit, and then they come in again. But crudely, you can think of this like a time axis. And then on the y-axis, we're looking at the difference in some property. In this case, it's the asymmetry in the light of the mergers relative to their control. So you'll always see that there'll be a horizontal dashed line to guide your eye that says if the galaxies in the mergers are normal compared to their control, they would lie along this dashed line. Okay, so here we're looking at this asymmetry metric, which we have quantified for all of the galaxies in Sloan. So for those of you who are familiar, this is the Samad et al. 2011 catalog where we do bulge disk decompositions, and then you can look at the flux that's left over once you subtract that smooth component. So that's your asymmetry. And so what you can see is that at wide separations, the galaxies have normal morphologies, but as they get closer and closer together, they become more and more asymmetric. So this is not surprising. It's something we already have intuition for visually, because we know that when we look at these interactions, they do seem disturbed. But this is a nice quantification of that effect, and it's also a nice demonstration that our control matching is working and that everything is leveling out when we get to wide separations.
How far out do you go in sort of half-life radii to do this asymmetry measurement?
So you mean for each individual galaxy? So it's measured to arbitrarily large distances because it's an extrapolation of a bulge disk. So you take the light that you can significantly detect, but then it extrapolates that out.
But the bulge disk bit is axisymmetric, so you're just looking at the leftover that's not.
That's right. Yeah.
Okay, but it goes all the way out.
Yeah.
I'm just wondering if you're weighting stuff that's like those kind of tails that are way out.
Mm-hmm.
Then you like to see the asymmetry closer in because that's where it's supposed to actually torque the gas to bring in.
Yeah. So you're saying it would be interesting to do it sort of as a function of radius within a given galaxy.
It's only weighted towards
Yeah.
the inset anyway because that's where the light is.
Yeah, so there are different asymmetry metrics that weight differently based on the distance from the center. So there's a separate metric, which is not the one I'm plotting here, that's called outer shape asymmetry. So this is just a flux weighted one.
So more or less what you want anyway.
Yeah, but you can do, yes, so you'll get a slightly different answer depending on how you decide to parameterize this. So if you used like a CAS or if you used a Gini M20, you get slightly different values. Yes, Peter.
Relative to this bias, how much dispersion is there in about that average asymmetry of the control?
Yeah, so you can see that in these sort of shaded areas here. So this is plus minus 1 sigma. So you've got either individual bin points or the solid blue line is a sliding bin. So you can kind of get a sense
But is that the
of that.
dispersion in the sample or in the control?
Both, because we're taking a ratio of the two. So we propagate those two things. Any more questions on that?
So presumably this distance where it starts mattering is something like 10 kiloparsec or something?
So it starts to kick in significantly around 40 or so. Yeah.
Okay.
But you'll see that the separation at which we start to see differences from the control depends very much on the thing that we're measuring. So for the asymmetry, we pick it up here. Now, of course, if we had deeper imaging, we would probably pick this up further out. So there's also an observational limitation in here as well. So what you should take away from this is that there is this general trend and that we're properly controlling such that we're getting to no excess at some wider separation. Okay, so now let's move on to the prediction of enhanced star formation rates. So we can measure these star formation rates directly from the Sloan spectra. So here, this plot is a very similar format to before. So we have the projected separation of the pairs. We now additionally have this gray box, which is for the post-merger sample. I didn't plot that for the asymmetry because the post-mergers are selected to have high asymmetry, so it's not really very meaningful to show that they are asymmetric. So this is the post-merger point here. And now our y-axis, rather than the excess in asymmetry, this is now the excess in star formation rate. And it's also now on a log scale, so our reference line is not at 1 for the ratio, but it's at 0 for the log. Okay, so what you can see is that there is clearly an enhancement in the star formation rate that we see in our pair sample, and that this enhancement increases as you get to closer separations, and that it peaks in the post-mergers. But if you take a look at the y-axis here, what you'll see is that the average enhancement in the star formation rate is actually fairly modest, factor of 2 or 3 at most. It's actually quite rare in mergers in the local universe, at least, that we get these very dramatic Euler type starbursts. Very few of our mergers look like that. You'll also notice that, in contrast to the asymmetry, we have not reached our kind of fiducial field value at wide separations. And originally, when we first made this plot, we worried a lot about whether this was a problem with our control sample, but it turns out we just hadn't gone to wide enough separations. So we repeated the experiment with all of Sloan, essentially now not limiting the maximum separation that we sampled, and we just found the closest companion for every galaxy in Sloan, so we could make this projected separation axis out to arbitrarily large distances. So the blue points are the results from the observations. So our original sample went out to 80 kiloparsecs, so you can see that's the enhancement that we are seeing. Now if we keep extending this to wider and wider separations, it's not till about 150 kiloparsecs or so that we start to have normal star formation rates.
So how do you actually do this star formation paths for measuring pairs of galaxies? So you look at each individual galaxy in that pair and see what its corresponding control galaxy is doing there.
Yeah, so it's the star formation rate of one galaxy in a pair, and then it's got, say, 100 control galaxies. So we take the average star formation rate of those 100, and then it's the ratio of those two things.
And this is for this huge range of mass ratios.
That's right. This is all in one. I'm not going to have time to talk about the separation of the mass ratio, but the short answer is that you can get boosts from both minor and major interactions, but you get the largest boost from the major ones. So you'll also see on this plot there are these red and black points, which in this paper, which goes back a few years now, this was led by Dave Patton in 2013, this was our attempt to do a comparison with the simulations at the time. Now, at the time, the simulations that we had available to us, or that we ran, so this is in collaboration with Paul Torre and Jorge Moreno, the tools that we had available to us and the way that it was generally done in the community was to use what are known as idealized binary mergers. So this is not a full cosmological simulation. You just take two galaxies, you merge them together, and you see what they do. You can also do this with zooms. So this is quite a popular way of doing it now, where you start with a cosmological volume, but then you just take a small box within that and then re-simulate at high resolution. So the advantage of the idealized merger suite, so we actually had 75 different mergers that went into our merger suite, is that you can pick exactly what you want in terms of the galaxy properties and the orbits of the mergers. So you can do very nicely controlled experiments by changing just, say, the bulge fraction of the galaxies or the orbits. But the problem is that you're not fully sampling the reality of the universe in terms of the broad range of parameter space. So this is something that is really only just becoming a reality, in that we can now use cosmological simulations that have full hydrodynamics and are done at decent enough resolution to start selecting statistical samples and comparing to the observation. So this is a paper that we've just submitted that uses primarily the illustrious TNG, but we've also done the comparison with other simulations such as Eagle, and we get qualitatively very similar results, where we can go into these large, relatively high resolution, full cosmological simulations and make mock surveys of pairs such that we can select our sample in exactly the same way as we do with the simulations. So this comparison is not really a fair one, because we have fine-tuned exactly what we wanted to go into these particular pair simulations. But when we select our mergers from illustrious, we just take, you know, the properties of the galaxies and the properties of the orbits that are coming straight out of the simulation. So here's the comparison again now, but using this full cosmological context. So once again, I'm showing you the Sloan results. So that's the red curve. So again, as a function of projected separation relative to a control sample. And then the blue is the result from the, it's called TNG 100. For those aficionados of simulations in the room, it's one of the flavors of the new illustrious model, one of their resolutions. So that's the blue curve. And the agreement is actually quite remarkable. So not only do they reproduce the same qualitative sense of an enhancement as you get to smaller separations, but the separation out to which you see that enhancement is very similar to the observations, and the overall normalization is also quite similar. We can also extend this into the post-merger regime. So this is the pairs, so we're only tracing these up to some small separation. So we can also do this in the post-merger regime. And this is work that's being led by one of my PhD students, Manhani. So again, using this illustrious TNG model. So here are the data from the pairs that I just showed you. So the axis now is flipped. So here they are coming closer and closer together. The star formation rate's getting higher and higher relative to the control. And then now we can switch to units of real time after the merger. And so you can see this peak in the star formation rate is now starting to die off. And so one of the main results here is that the enhancement in the star formation rate dies away within about half a gigayear or so. So it's not terribly long-lived. One of the experiments that we have yet to do, but I think will be very interesting, is to essentially integrate under these two curves to understand which phase of the interaction is most important for your overall star formation budget.
So you're comparing the controls, and those controls look like ellipticals afterwards, or not?
So we haven't done the morphology yet. So this is still... That's right. It doesn't seem to die away. Yes, that's right. So hold that thought, because this question of whether mergers lead to quenching, I think is a picture that we have in our minds, but maybe not one that's actually borne out in either modern simulations or in observations. Okay, one thing I haven't talked about yet is measuring the chemistry in these interactions. So remember, I've talked a lot about these gas flows pouring into the center of the galaxy. So that is going to carry material from the outer disk towards the center. And that outer disk material is more metal poor than the material in the center because of the abundance gradients in the galaxy. So again, prediction from the simulation is that you should dilute the central gas phase metallicity during the interaction. Sloan gives us a very convenient way of measuring this observationally, because there is a 3-arc-second fiber, which corresponds to about 2 kiloparsecs at the typical distance of Sloan galaxies. So the emission lines that we measure in that fiber are indicative of the central gas phase metallicities. So once again, we have the separation of the pairs, we have the post-mergers, and now our offset metric is the gas phase metallicity. So here's our fiducial line for where the galaxies should be at if they were same as the control. So now we see that the mergers in the pair phase are low, as predicted from the simulations, and that they get more metal poor as they get closer together. And they are most metal poor in the post-merger phase, which might seem a little surprising, because you might think all this star formation that's going on should re-enrich the interstellar medium after the supernova. So I think what this is telling us is that our particular post-merger selection in the observations, which if you remember is basically by eye, looking for train wrecks, is catching the post-mergers quite early after their coalescence. If we had a sample that was able to look at much older post-mergers, maybe we would start to see this re-enrich. And that's certainly something we plan to do with the illustrious simulations, to see what the timescale is for the metallicity re-enrichment.
Could you also look at different elements, because the enrichment timescale is different?
Yeah, it's in the Sloan sample, it's quite difficult to do other elements. Oxygen is the one that we most readily have available. But you're right. If you could look at, for example, the oxygen to iron ratio, but unfortunately, it's very challenging to do those other abundances, at least with the Sloan spectra. Okay, next I want to talk about triggering of AGN, which has actually been quite a controversial subject in the literature. But I'm going to show you a few sets of results that I hope will convince you that we do know the answer to this. So there are two ways you could think of setting up the experiment to test whether there is a connection between mergers and AGN triggering. The first way you can do this experiment is to start with your merger sample and to quantify the number of AGN you have in your mergers and your control, and look for an excess very similar to the previous plots that I have shown you. So This figure is doing just that experiment, but it's doing it 3 separate times, selecting AGN in 3 different ways. So AGN are a multi-wavelength phenomenon. You can select them in the X-rays, you can look for radio jets, you can look for heating of the dust torus, and these different selection techniques at different wavelengths actually select different AGN. Okay, it's not all the same sample. So that's an important caveat. So let's first of all do it using a selection based on optical emission lines. So this is very easy to do with the Sloan spectra. You measure the strength of strong nebula lines, and you can use the ratios of these different ionization lines to tell you whether there is heating from an AGN. So we can count the frequency of optical AGN in our mergers. We count the frequency of optical AGN in our control. We divide one by the other, and we measure this AGN excess. So again, very similar plots, projected separation, post-merger, excess. All right, so what we see is that as the galaxies get closer together, they start to show an excess of these optical AGN, and there is this steady increase in this AGN excess that peaks in the post-mergers, such that in that late stage, you have a factor of 3 to 4 more optical AGN in your mergers than in your control. And it's very statistically significant. You can repeat that experiment, but yeah.
So this, remind me what in your control, what fraction of equate objects are optical AGN?
About 5%.
So this goes up to 15%.
Yeah. Yeah, so it's not, they're not all AGN.
Right.
Yes.
So that's already kind of interesting. Like most of them don't show any AGN.
That's true, but hold that thought. All right. That number is actually quite different for the mid-infrared, a higher fraction. So in the mergers, we get about almost 50% are mid-infrared selected AGN. But an important thing, so I think this is for 2 reasons. One is that I don't think all mergers will trigger an AGN. So if the orbits aren't right, you don't get these gas inflows. But secondly, the AGN is stochastic. And so just because it's not on at this moment doesn't mean it hasn't been on or won't be on again. So an interesting question, but one that's very difficult to quantify observationally is, you know, if you were to survey the interaction, for example, in the simulations, what fraction are on?
You shouldn't believe the simulations.
I'm glad you said that, not me. All right, so the mid-infrared selected AGN. So this is done by cross-matching Sloan with the WISE all-sky survey. So WISE operated in 4 mid-infrared bands, and you can use the colors from these mid-infrared bands, again, to infer the presence of an AGN through the heating of the dust torus. So you can see the same qualitative pattern, that there is an excess of mid-infrared selected AGN that increases as you get to closer separations and peaks in the post-merger stage, but the y-axis here is different. So this is a factor of 4, this is more like a factor of 12. So the flavor of AGN that you seem to more readily get from an interaction is a dusty, obscured one. And this is consistent with other works that have used, excuse me, for example, measurements in the hard X-ray, that they find that mergers very often have highly obscured AGN in their center.
Just a question on the mid-IR AGN.
Yeah.
There's a huge step up from very close separations to the post-merger phases. Do you have an explanation for that?
I think it's just that by the time you're in this post-merger phase, that's when the mess is full on. And so in order to get these obscured AGN, you have to have 2 main ingredients. You have to have a bolometrically luminous AGN, and you have to have a high NH and a high dust. And we actually had a paper, I didn't include a slide on this, that was led by Laura Blecker, where we, again, modeled from simulations, including radiative transfer, so we can actually predict the colors, the mid-infrared colors, and we see exactly the same thing. There's a big step function in the post-merger phase, that's where, yeah, you get a high covering fraction of this obscuring material, and the AGN is bolometrically dominant over the star formation as well. This third panel is now selecting mergers in the radio. So it's a particular flavor of radio AGN called low excitation radio galaxies. And what we find there is a very different story. There is no difference in the frequency of these lurgs So where LIRG is low excitation radio galaxy, not luminous infrared galaxy. There is no excess of this radio AGN population. The post-merger point looks high, but the error bars are large and consistent with no offset. So it seems as if this flavor of AGN is probably secularly triggered. So one of the things you should take away from this slide is that mergers can trigger AGN, but not all AGN are triggered by mergers. This is the first way you can do this experiment. But there is another way you can do this experiment, and that is to start with an AGN sample and look to see how frequently the AGN hosts are disturbed. So this is a subtle twist coming at it from the opposite way. So we recently did this experiment using the Canada-France Imaging Survey. So for those of you not familiar, this is a large survey with the CFHT. It's still ongoing. Eventually, it's going to cover some 5,000 square degrees of deep R-band imaging down to about 27.5. So it's deep, and it's also very high imaging quality. Typical full-width half max is about 0.6 arc seconds, so much better than Sloan imaging. So what we did was we now flip the experiment. We select all of the optical AGN and all of the WISE AGN that are in the current Sloan CFIS overlap. It's about 2,000 square degrees. And then we visually classified those hosts into whether they were isolated, had a close companion, were interacting, or if they were in post-mergers. So now this plot is quite a different format to what you've seen before, but we still have an excess on the y-axis. That's what you should look at. So this is basically saying in any of these different morphology classes, do we have more AGN than non-AGN? So maybe let's just focus on this last column because it encapsulates the main result, which is that both for optically selected and for mid-infrared selected AGN, you have a factor of about 2 more disturbed galaxies in the AGN hosts than in the non-AGN. So we have a non-AGN control sample here. So in summary, it doesn't matter whether you start with AGN and look for an excess of disturbed morphologies, or if you start with mergers and look for an excess of AGN. You see the signature in both experiments.
Is it is it significant that post-mergers are probably lower than the interacting pairs? In the sense that the AGN turned on very quickly?
So you mean the difference between this and this? Yeah, we were a bit surprised by that because the first way of doing the experiment seemed as if it would predict the opposite. It's not, you can't perfectly match these two experiments because, so for example, imagine just if you repeat this experiment with an imaging survey of different depth, so you become more or less able to see these morphology features. So the actual number of galaxies that look morphologically disturbed is going to be sensitive to these selection biases. So the raw numbers, and likewise when you do it this way, for example with the mid-infrared selected AGN, where you draw the threshold in your color cut also can change this number quite a lot. So it's more the qualitative trends that are important than the raw numbers, which are down to how you choose to select either your mergers or your AGN. Okay, so we've worked our way around here. We've looked at metallicities, star formation rates, and AGN, all of which seem to, at least qualitatively, be consistent with the predictions from the simulation. So at this point, maybe the simulators in the audience are kind of feeling a bit pleased with themselves. However, there's this whole second part of the diagram that remains largely untested. So we were certainly not the first to look at star formation rate changes, and we were not the first to look at AGN. I would argue we probably did it with larger statistics and with more careful control matching, but really no one has looked in detail at this second part of the diagram. And so that's what I want to focus on now for the rest of the talk. So the first thing we want to test is this prediction of gas blowout. And this is a really important phase if it exists, because this is then the death knell for the galaxy. If you remove the gas, it's not going to be forming any more stars. So we made our journey through looking for this blowout in a few steps. So we couldn't use Sloan to do this because we need to measure the gas content. You don't get that from optical spectroscopy. So we needed to obtain new observations to measure the gas content in our merger sample. So we started off very modestly with just 11 galaxies selected from our close pairs sample. And we obtained observations of CO from the IRAM 30 meter. So here are some of our spectra, and we had learned from our earlier Sloan work the importance of the control sample. So we have a control sample from another CO survey that was done by one of our collaborators. And so we can use exactly the same pipeline. We do all of the observational shenanigans in exactly the same way. So things like aperture corrections and the choice of oh, we shenanigan. Actually, I don't know if you could make that a verb, but I'm sure, yeah, we shenanigan too. There are many things under the hood that observers don't tell you about. So all of this is done homogeneously for our 11 galaxies in pairs and for our control sample. And so we can compute this offset metric, or XS, as you've seen for the other parameters. So now we're going to be measuring the mass of the molecular gas. So we convert from our CO to H2. And so this delta quantity, you've seen delta star formation rate, you've seen delta metallicity, is now for the gas mass of the galaxies in the pairs relative to the value in the control. Now, I only have 11 galaxies, so I'm not going to be so cavalier as to show this as a function of projected separation, because I don't have the statistics of that. I'm just going to show you a histogram. I'm going to show you a histogram of this offset metric, which, recall, if you've got the same molecular gas mass in your pairs as in the control, this value should be 0 because it's on a log scale. Okay, so here's what we get. So the red histogram, that's our 11 galaxies in the pairs. Here's what we would expect if they had normal gas masses. Here's our underlying control sample, which is nicely symmetric around 0. And what you can see is that we find no evidence for removal or reduction or consumption of that molecular gas, which would be a negative delta gas mass. On average, we find that the gas mass in our 11 pairs is actually higher by a factor of around 2. Right? So we're not removing it. There seems to be more of it. Okay, this is only 11 galaxies. Maybe this is small number statistics. So we did it again with a larger sample. So now almost 60 galaxies. This is a paper that was led by Xian Pan at Asia A, where we combined some archival measurements, some of our own PI programs, some from the Jingle survey. And here is the same histogram. So we did basically the same approach as in the previous paper. So we can measure this delta gas mass. Here is 0. Here is in yellow our pairs. And you can see there is still a shift to positive values. So this seems to be quite statistically robust, that there is an excess on average of a factor of 2 molecular gas in this interacting sample. Okay, so no blowout, but maybe what we're seeing here is that we have to fuel these starbursts in some way. So maybe the gas in the molecular phase has been taken from the atomic phase, converted into molecular gas, and that's what you're going to be fueling the stars with. So if we want to see blowout, maybe where we should be looking is in the atomic phase. Okay, so we did that. This is now not with a pairs sample. This is now with a post-merger sample, partly for observational ease, because if you want to measure the atomic gas, you use the 21 centimeter line. We were using Arecibo, which has got a massive beam on the sky, so you can't separate individual pairs. So to make life easy for ourselves, we just chose the single post-mergers. So we have about 100 that in our sample. About half from the archive, about half that we observed ourselves. Again, we had a control sample from a survey that was led by one of our collaborators. So again, same pipeline, same corrections, et cetera, everything consistent between the controls and the post-mergers, so that now we can do our atomic gas fraction differences, okay? Once again, everything seems to be, I shouldn't say everything, almost everything seems to be rich in atomic gas, not reduced in atomic gas. So in the observations, we have not seen any evidence for massive gas removal or wholesale consumption of the gas. There is more of it in the mergers than in the control sample. So this makes you wonder, yes, Alison?
I'm just curious to know if you've looked at the molecular to atomic hydrogen gas.
So unfortunately, our samples don't overlap because this is post-mergers and the pair work was in the molecular gas. We do now have a post-merger sample in CO where there is some overlap, but we haven't finished with that project yet. But eventually we will be able to do that, but we can't do it with the data that I'm showing you here. So then it's maybe time to revisit this idea of what the gas in the mergers is actually doing. So the simulations from, 2008, the simulations have come a long way in that decade. So in a paper earlier this year led by Jorge Moreno, we ran a new suite of simulations using a different code. Many of you here will be familiar with the FIRE approach. And so here we traced during the interaction, so we had a suite of about 25 different mergers, different galaxies, different mass ratios, different orbits, and we traced as a function of time how the gas in the different phases, so you can draw your favorite divisions on a phase diagram, how the gas in these different phases changes. And what Jorge found was, sure enough, relative to his own control sample, which is this horizontal line, there is an increase in the cold molecular gas phase, a smaller increase in the atomic phase. So the numbers don't match the observations, but the qualitative sense of what he was seeing is that you are depleting the warm ionized phase, cooling it, and then building up these two cooler phases. So some at least qualitative consistency with the observations. Now, just because the gas isn't blown out doesn't mean it is not significantly rearranged. So this is a paper from last year, led again by one of our PhD students, Manhani, who was interested in looking at how the merger affected the gas in the circumgalactic medium. So now looking out to separations or galactocentric radii of 150, 200 kiloparsecs. So this was just a single zoom-in simulation, so just one single case study. So as a function of time, what Man was doing was tracing the covering fraction of gas above a certain column density limit. So this is the way that observers often do it in their surveys. So for example, you can take the blue line, so this is saying what fraction of sight lines through my galaxy have a column density above 10 to the 21 atoms per square centimeter, and then different thresholds in the different colors. The vertical dashed line here shows the moment of coalescence. So this is the pair phase, this is the post-coalescent phase. So what Man found is that you enhance the covering fraction of your halo gas out to these large distances, 150, 200 kiloparsecs or so, and that gas can stay out there for a long time. So the mergers can have a very significant impact on populating the gas in this circumgalactic medium. And it's not just the hydrogen gas, it's also the metals that get redistributed. So this is now measuring the change in the metallicity during the interaction at different distances in the galaxy. So this blue line, this is essentially showing you what's happening in the disk. And so the metallicity dips during the merger. So that's the prediction of the gas, the metal poor gas inflows that we're seeing. But what you can see in the outer CGM is that metals are actually pushed out there by winds. And so mergers turn out to be quite an effective way of populating the CGM with metals that lasts for a very, very long time.
So what's the X-ray luminosity that you would need for the gas to cool?
I'm not sure I understand what you mean. The X-ray luminosity you need.
If you go back from those slides,
oh, you're not talking about this. Sorry, you're talking about this. Yeah, okay.
So there's a deficiency of warm There's a medium and a surplus and covalent. So what is the luminosity that you need?
That would be a negative. That would be the UV optical number.
Are you talking? Yeah.
It's too cold.
Yeah. This is X-ray here. This hot stuff. Yeah.
So the hot one is obviously.
Yeah. So the hot stuff is. So there's also an increase in this very hot phase as well. So the gas undergoes multiple phase transitions, so it's not that everything piles up in one phase. So some gas is heated, some gas cools. It depends where in the galaxy it is.
So
But in terms of the wavelength regime, yeah, this is the X-ray stuff here.
So there's no radiated cooling here. You just transfer heat from one phase to another.
No, it can cool.
So what
It can cool, which is why you can get an increase in the cold phase as well.
So is it? And what's luminosity did you need?
So are you asking me what is the X-ray luminosity I would expect to see?
Because I thought you get rid of the hot one, but if you get rid of the warmth, then it's UV. So what's the UV luminosity?
So you're asking me what is the deficit in UV luminosity I would expect here?
Well, why deficit? You need to cool, right? So you need to emit more.
So you're looking for the cooling signature. Okay, I don't know the number. I have no idea what the number is. Yeah.
It's tiny compared to the luminosity
Yeah.
of the galaxy.
I mean, the galaxy is forming stars and has an AGN. Yeah.
Nobody can see this.
Yeah.
In
Yeah.
KCWI, you can maybe see some of the stuff farther out, climb down a little bit. You know, you can see
It's
the
too even
things.
more but if it was so X-rays, then you might see it.
Nobody can see X-rays now. These are all L-star galaxies.
Yeah, yeah.
You can't see the X-rays from those.
Yeah. But I don't know what the actual luminosities are. Okay, you guys ask a lot of questions, so I'm going to kind of keep talking and assume that the question time is wrapped in with the talk time. All right, so this is the last section of the talk now. So up until this point, we have talked about integrated properties of galaxies. So either a single fiber measurement or a total gas mass. But what we would really like to be able to do is spatially resolve what is going on in the observations. So this is important, for example, if we want to test the prediction that the action is going on in the center of the galaxy. Like, is the star formation truly centrally concentrated as the simulations predict? And fortunately, we can do this nowadays because large resolved IFU surveys are now coming online and have large public data sets. So I expect many of you have already heard about the Manga Survey, which was this very clever idea from the Sloan people, where they were going to take their individual fibers, bundle them up into these hexagonal IFUs. So now when you place this bundle over an individual galaxy, you don't just get one spectrum, you get spectra over the entire face of the galaxy. So you get these nice hexagonal maps, hexagonal just because that's the shape of the bundle, where any property that you could measure in a single fiber, star formation rate, gas velocity dispersion, stellar ages, masses, you now get a map over the entire galaxy. So we have been selecting, or we are starting to select mergers from Manga. So the first 5,000 or so galaxies from Manga are now publicly available. Eventually it's going to be 10,000. And so this was done actually with an earlier and smaller data release. This is led by another of my students, Mallory Thorpe, where she went through the Manga sample and she visually identified the post-mergers. So there's a sample of 36 that she found, that she is now hoping that she can look at radial gradients. But we need a different metric now, because now we're looking at individual, what we call spaxels, so spectral pixels. Every pixel is going to be a spectrum. So how are we going to measure this, and how are we going to compare it with the simulations? Well, the simulation part was already done a few years ago. So this is another paper led by Jorge Moreno, where he looked again at this suite of galaxy mergers in an idealized sense, and he measured, this again is a metric of the star formation rate change compared to a control. But now the x-axis is not the separation of the galaxies, it's the distance from the center within a given galaxy. So each curve here is a different galaxy. So for example, you can look at the blue solid line. So this is a galaxy for which within the central few kiloparsecs, you have a boost in the star formation rate relative to this. But in the outer parts, you have a lower star formation rate than you might have expected. And you can see there's quite a lot of variety here. Although most of the galaxies show enhancements in their central regions, there's quite a bit of spread. In the outer regions, there's a lot of variety. Some of them have suppressed star formation rates, some of them have normal, some of them have maybe still moderately enhanced. So we have at least a prediction to compare with, but we also need a metric that is going to allow us to do this in the observations. So I'm just going to briefly explain how we do this. This is a figure that contains 500,000 spaxels from Manga. So it's a density plot. All right, so the colors tell you how many spaxels there are. And it's measuring how much stellar mass there is in your spaxel and how much star formation rate there is in your spaxel. This relationship has been found before several times in earlier surveys, and it has become known as the resolved star-forming main sequence. So many of you will be familiar with the idea of the star-forming main sequence, which is total stellar mass, total star formation rate. This is on a kiloparsec scale within the individual spaxels, where we're measuring the surface densities of the stellar mass and the surface densities of the star formation rate. But there's this overall correlation. So you can think of it that if you know how much stellar mass is in your spaxel, you can predict how much star formation there should be in your spaxel. So for any given spaxel, you can see where it lies relative to the ridgeline and compute this offset, which is this combination of Greek letters that is the delta sigma SFI. It's a bit of a mouthful. So if this delta sigma SFI is negative, it means you've got less star formation in your spaxel than you would expect. And if it's positive, you have more star formation in your spaxel than you would expect. So now we can try to make radial profiles like this in the Manga data. So this is these are the results from Mallory's paper that we published earlier this year. So each curve is one of the 36 post mergers. So this is exactly analogous to what was done in the simulations. And you can see there's a lot of variety. There was a lot of variety. Most of the post mergers have high star formation rates in their center. So here's that delta star formation rate measure relative to the norm. So we're going out to about 1.5, in some cases 2 RE. So on average, these are elevated, but there's quite a bit of variation in the outskirts. Some have got these low star formation rates, like Jorge was finding, but quite a few others have got elevated star formation rates all the way out. And if you take the average of those profiles, this is what you get. So in the post-mergers from Manga, we do find these centrally peaked central star formation rates. But on average, we find that there is an enhancement in the star formation rate all the way out to at least 1.5 effective radii. Now, you can also do this work for the broader galaxy population, not just for the mergers. And that was something that we did in a paper last year, where we took slices through the global main sequence. So we could choose passive galaxies with very low star formation rates globally. And we could take starburst galaxies with very high global star formation rates and ask where in the galaxy were those star formation rates being regulated. So for example, the passive galaxies that lie far below the global main sequence that have very low star formation rates, we found that their radial profiles were such that they had low star formation rates all the way out to 1.5 RE, but it was really the center of the galaxy that was driving the bus. This is where the biggest dips were in the star formation rates relative to the norm. Likewise, we could pick starbursts. So these are not necessarily merger-driven starbursts. In fact, very few of the galaxies that go into this average profile have a companion or look disturbed. But you see a very similar profile to the merger one, which is an elevation in the star formation rates all the way out, but one that is centrally peaked in the center. So the question that arose from the combination of both the merger work and from this starburst work was, what is driving these high central star formation rates? You could think of two simple scenarios. I've talked a lot about gas inflows, so maybe you're just putting a lot of gas into the center, and so you've got more fuel for star formation, so you make more stars. Alternatively, you could have a similar amount of gas and just be much more efficient at converting that gas into stars. So the star formation efficiency is going to depend on, local environment parameters such as the local pressures, what the turbulence is. So maybe that's what is driving this. So to answer that question, now we need to combine the resolved maps of the stellar properties and the star formation rate that we get from Manga with maps on the same spatial scale of the gas. And so I'm very excited about this new survey that I'm leading with Li Hui Lin, which is called the Alma Quest survey. So this is 46 galaxies selected from Manga, where we also have Alma CO1 observations. So here are just 3 examples where you can see we have maps from Manga in the star formation, in the stellar mass maps and the star formation, but then we also have the maps of the molecular gas from Alma so that we can get maps of gas fraction and star formation efficiency. So I'm just going to give you my last slide, which is a paper that's just submitted now, which is then trying to understand whether it's enhancements just in the gas fraction that are driving these central starbursts, or changes in the star formation efficiency, which is essentially how much more star formation you have for your gas. So this is the Kennicutt-Schmidt relation. The spaxels scatter around this. So this scatter is our measure of change in star formation efficiency. And what we find, I'm sort of summarizing the entire paper in this one figure, is that the star formation efficiency is much more strongly correlated with the changes in the star formation rate. So you can see most of these star formation rates are high because they're these starburst galaxies that we've selected. There's correlation with the star formation efficiency that's much stronger than the correlation with the gas fraction. So from this sample of Alma Quest, of which a dozen of these central starbursts, it seems to be that star formation efficiency matters more than the excess gas. Okay, so I will just leave you with my summary and ask if there are any more questions. Thank you very much.
So back when you were showing us the histograms.
Of which, sorry, the total gas?
It was massive H2, for
Yeah.
example, and so on. You had some other histograms on those.
This?
No, probably one.
Oh,
There were a whole bunch.
yes, yeah.
So you got one for star formation efficiency and star formation rate and so on. But this is in the bulk, not spatially resolved.
That's right. And the other thing to know is that the matching here is done in a, so the matching with the control sample here requires that the control has the same morphology and that it be star forming. So you haven't matched the star formation rate, but you've required that your controls have similar star forming properties here. So if you do that, you find the star formation efficiencies are quite similar. So what that means is if you can get high gas masses and high star formation rates for reasons other than mergers. So it doesn't have to be a merger to give you a high gas mass. So put another way, galaxies that are above the global main sequence, some of those are mergers. Those mergers have high gas fractions, but other galaxies that are up there have similar properties. So the star formation efficiencies turn out to be the same because you've said the star formation rates are high and the gas masses are high. If that makes sense.
Can you pull apart the information that's in these histograms and just do scatter plots to see if the ones with higher mass of H2 have higher star formation rather than in this histogram?
I sure can. So this is now the individual points. So in this case, this is plotted by projected separation. But yes, you could take, to see whether there's a correlation between your delta F gas and your delta star formation rate. And there is no correlation between these different offset metrics. So it's not quite as neatly packaged as, because you have a high star formation rate, your gas is doing something in tandem. I think it's because the timescales for the different processes are likely to be different, and so it's not coordinated enough. At least so this is still only 60 galaxies. Maybe if we had a larger sample, we'd be able to pull something out from the scatter, but we don't see it here.
Great. Any last questions? If not, then we won't do cookies upstairs, because we're taking Sara out to lunch now. So let's thank her for a great